Okay, today I'd like to do our third main day of relativity notes. I want to remind you this is Einstein's special relativity, special meaning that it only applies to frames of reference that are moving at a constant velocity. In this special relativity, we have one principle that we must make sure we understand, and that is that the speed of light is the same in all of these non-accelerating frames of reference. If that is true, and all evidence seems to point that it is true, then time is no longer invariant. That means a person on a ship will measure a different amount of time than a person on Earth when viewing a certain event. So the event we looked at was a laser beam going from the bottom of the ship to the top. We saw that the guy on the ship saw a small distance. The guy on Earth saw a larger distance. And now we notice that if they're going to have the same speed, but they have different distances, they must also have different times that went by. So the time on Earth is different from the time we view passing on the ship. The time on the ship that we see is less than the time on Earth. Consequence number 2 is also pretty weird, so let's take a moment to draw this out. You have a person on a ship moving at a speed relative to the Earth of 0.9 c, and we have a person on Earth, and we have Mars, and at this moment Mars is about 18 light minutes away from the Earth, meaning it would take light 18 minutes to traverse the distance. Okay, and here's what I'd like you to do. Just like we did before with time, I'd like you to have two different views, an Earth view, and on the Earth view, again, we're not looking at light, we're watching this ship. So on Earth, they see the ship traveling at a speed of 0.9 times the speed of light. They see a distance between Earth and Mars of 18 light minutes. So notice how we're writing this. The speed, we're going to keep it in terms of light. And we'll say it is 0.9 times the speed of light, and the distance is 18 light minutes. I know this is weird in terms of the units, but it will work out easy if we realize time will be in minutes. Okay, so when we solve this, the c's cancel, we move stuff around, and we get that this takes 20 minutes. The guy on Earth would see this ship take 20 minutes to travel from the Earth to Mars, traveling at that speed. Now look at it from the point of view of the ship. Remember, the guy on the ship doesn't know he's moving. The guy on the ship thinks he's at rest, and he sees the frame of reference containing the solar system objects, the Earth and Mars, moving in the opposite direction at a speed of 0.9 c. Remember, they always agree on the relative velocity of the frames, but they disagree on other things. Okay? So again, the guy on the Earth thinks the ship's going to the right. The guy on the ship thinks the Earth is heading to the left. So from the ship's point of view, it would say velocity equals distance over time. They have to have the same laws of physics. The speed of the Earth is 0.9 c. It takes 8.72 minutes. How do we know that? Because we could use the formula that we had last time, where we had time on the ship, time on the Earth, radical 1 minus v squared over c squared. And if we plug 20 minutes of Earth time, that would give us a ship time of 8.72. So then when we solve, we notice that the guy on the ship sees the distance between these two planets as 7.85 light minutes. I want to take a moment to make sure I understand what we just said. These two people disagree on time. We already knew that. But now they disagree on distance. The guy on the Earth sees this distance as 18 light minutes. A certain number of meters. It's just easier to work this way. The guy on the ship sees this as a much smaller distance. Distance, lengths, are no longer invariant. The person on Earth sees a certain gap in terms of distance. The guy on the ship sees a totally different distance. Notice the guy on the ship sees a smaller distance than the guy on Earth. So they would both describe this totally differently. The guy on Earth would say it took the ship 20 minutes to travel this distance. The guy on the ship would say, no, it didn't. It only took me 8.72 minutes to travel this distance. But they would both agree that the guy started here and ended here. They just measure that as a different distance. They would also agree that they were traveling at a relative speed of 0.9 times the speed of light. Okay? This is our second consequence. Distances are no longer invariant. Here is the new formula that will actually predict this. Okay, so we have length in one frame is equal to the length in the other frame times our familiar radical. 1 minus v of the ship squared over c squared. Realize this doesn't have to be a ship. It is the relative velocity between the two different frames of reference. Some notation I want to make sure you understand. We're not going to call them length on Earth and length on the ship anymore. We want to get a little more sophisticated. We're going to call them LO and L. LO stands for what's called, and this is official terminology, the proper length. And this length is just regular old length. So what makes it proper? Because after all, we already said that all frames of reference are equal. So now all of a sudden, why are we saying this one's special or proper? Well, what we mean by proper length is the length measured by someone at rest relative to what's being measured. So when we look at this distance from Mars to the Earth, this guy is in that frame of reference. He's part of that solar system frame of reference. So he measures the proper length between those two. The guy on the ship is not part of that frame of reference. He is moving relative to that frame of reference. He sees that frame of reference moving relative to him. So the guy on the ship is measuring a moving frame of reference. He would see L. So LO in this case would have been the 18. And then we'd use radical 1 minus 0.9 squared. Again, we use the trick that the speed of lights are going to cancel. And this should come out to give us the same answer we had from the other method. So again, length gets shorter when you're looking at a frame of reference that is moving. Okay? Realize it works the other way too. So if we talked about the length of this spaceship and we said which of these two people sees the proper length of the spaceship, I hope you see it's this guy in the ship. The guy in the ship is part of the frame of reference being measured. Okay, so he would measure the proper length. The guy on Earth would measure a shorter length. What this means is when this ship goes passing by, the people on Earth would see that ship shorter than the guy on the ship. The guy on the ship would measure a value for length. The guy on Earth would see a smaller distance or length for that ship. Again, who's right? They're both right. They both are equally valid. We call the length measured by this guy the proper length only because he is at rest relative to what's being measured. But both lengths are equally valid. Okay, so we started out, we had 18 minutes. We had a speed for the 2 frames of reference of 0.9, and we found that it took 20 minutes to travel as viewed from Earth, and that the guy on the ship saw this length as 7.85. So again, they're disagreeing on how much distance there is between these 2 planets. The guy on the ship sees it smaller. What if he had been moving faster? If we do the math, we find that he sees the distance even smaller. And if he's moving really fast, it gets smaller still. I hope you see what's coming. As we get closer and closer to the speed of light, the distance between these 2 planets becomes smaller and smaller. When we hit the speed of light, that distance approaches 0. Okay, so here we're at 0.9999 C. If we look at our formula, I hope you see that if we put in the speed of light up top, we get a fraction of 1. 1 minus 1, 0. Square root of 0 gives us 0. So no matter how much distance the person on Earth sees, the person on the ship sees a distance of 0. What does that mean? It means to that guy on the ship, the Earth and Mars are touching each other. There is no distance between those 2 planets. He is measuring 0 distance. In fact, all objects in that direction of motion would have a distance of 0. How is that possible? Well, remember, when we watch that guy pass us by on this ship, if he's traveling at the speed of light, his time stops. So for him, the Earth and Mars, he passes them simultaneously. There is no distance between them because it took him no time to get from Earth to Mars. No time, no distance. No problem, I hope. Okay, so there again is our relationship. The faster we go, the smaller the objects get. And you can see that it starts out real gradual, and this change in length starts to get really, really rapid as we get closer and closer to the speed of light. One last thing before we end that I want to make sure is clear. And that is this contraction in length only happens in the direction of motion. So this ship is moving to the right, so it will shrink horizontally, but the height of the ship and the depth of the ship will not be affected because it's not moving in those directions. So this length contraction only happens in the direction of motion. Okay, before we end today, I wanted to just share something with you. Hopefully you'll share something back when you do your work today, or if not today, the next time. And what I wanted to show you was I got my first harvest of strawberries. It's not a lot yet. Hopefully we'll be getting more. But you see how good they look. And I also was able to harvest and eat the first broccoli, and that turned out to be really good. So anyway, guys, have a great weekend, and we'll see you on